display devices and any other I/O devices you can interface to 8086 through ports. So then we try to see what exactly is the port and then how to do interfacing I/O devices with 8086 is what we try to see in these particular classes. So in the last class we have seen how memory can be interfaced. So in detail is what we try to see in the first half an hour, and then the next 1 hour we'll try to discuss ports and then what exactly the port, and then we try to interface 8255 to 8086 is now. So in the last class we have seen memory interfacing. So this chip select should be low if you want to access a byte or if you want to write a byte into the memory. So write enable is write something into the memory. So for 8086 based systems we need even memory and odd memory. So D0 to D7 of the processor is connected to the data bus of memory, and D8 to D15 of the 8086 processor is connected to data bus of the memory. So D0 to D7, so these are 8 pins, these are 3 pins, and it is 64 by 8. So it is 64 by 8 size, it means 64 kilobytes of memory. So we need 16 address lines, 16 A0 to A15, 16 address lines it has. 16 plus 8, 24, 24 plus 3, 27 pins it has, plus VCC and then ground. Right? So now if you try to see, so this is VS2, it is connected. So this is how we do the connection. Now the 16 address lines of the processor A1 to A16, here you have to remember, you should not connect A0 of the processor to this memory. You should not start from A0. Why? Because A0 is used to select lower memory address, okay, lower memory bank, and BHE signal line of the processor is used to select odd bank of the odd bank memories. So A0 you should not. So you need 16 address lines. So processor has 20 address lines. So A1 to A16, 16 address lines from the processor is connected to the address lines of each memory ICs. Right? So then what about the remaining A17 to A19 means remaining address lines of the processor. So here in this case, this is what we discussed in the last class. So design a decoder for 8086 SRAM memory interface on the figure shown, such that the memory is mapped to the address range of 0000 to 1FFFFH. So in this case, when we have seen like 0000, when you consider, here you have, so here you have, this one is A19, A18, then A17, and this is in the case of 000, and then this is in the case of 1FFFF. So now if you consider this is 1FFFF. So here in this case, this any point, this A19, A18 and A17 are 0. So this can be, that means whenever there is 0 on these pins, then that memory particular IC is activated, is what we can write. So we can give it to a OR gate. So it is an OR gate. So when these two are 0, these three are 0, so then output is 0. So then this can be connected to chip select lines. So what is there in this block box? Here is this decoder IC, means this is what the internal circuit. Here you can have an OR gate. So this OR gate can be given to here. So whenever there is a 0, 0, 0 here, the output is 0. So when it is 0 and 0, the output is 0 means even bank is selected. And when it is 0 and then when BHE is 0, then odd bank is selected. So this is how we can do the memory mapping. Let us continue our discussion how to interface the memory mapping in these cases. So now this is an example. Interface 216 kilobytes of memory chips to 8086 to a mapping address from 000002 to 7FFFFH. So here it is very clear problem. So now what you can do is your RAM could be of 32 kilobytes, 16 KB, 16 KB. That is what you interface to 8086. And when you are doing the interfacing this to 8086 and the address which you give, so here you will be very clear. This is what your microprocessor, and here is what you are going to connect your memory, but the memory address should be this. Okay, so here is what you are going to connect your memory, and the memory address should be this. So then here you need to design an interfacing circuit so that when the processor releases this address, that particular byte, any byte from the processor can be written into the memory, or any byte from the memory, it can be fetched by the microprocessors. So now this circuit, if you try to see, as an example, as a beginning, if you try to see, is 16 KB and 16 KB. So two memory chips are there, 16 KB and 16 KB, right? And now here you have a RAM IC. The RAM IC is 62128. 62128 is a two RAM ICs you have. So then it is 16K. So 16K means how many? K means 10. 16 is 2 power 4. So 2 power 4 and then 10. So you have 14. So you have 14 address lines with the memory IC. So you have 14 address lines of the memory IC. And it's a 16K byte, means KB, kilobytes, means at a time you can read or write a byte from the memory. So you have D0 to D7, right? So this D0 to D7 you can connect it to, so if you can consider this as a even bank, so then you can consider this, so then you have even bank and odd bank. So as we discussed, the memory of 8086 are divided into two segments. So you can give, sorry. Here, here it is, it is connected here. So D0 to D7. So then you can think of this to be even, this to be even, and this IC can be of odd, right? So now, so this is even bank. So D0 to D7 of this one is connected to D0 to D7 of the processor, and D0 to D7 of this one is connected to DA to DA15 of the processor. So data bus is connected to data bus of the memory. Data bus of the microprocessor is connected to data bus of the memory. And to connect here 16K kilobytes of memory, you need 14 address lines. So then you cannot use A0. Remember, A0 is lower byte or even bank selection. So A0 is straight away can be used to an OR gate. So whenever this is 0, this memory should be activated or enabled. So here we can say, like, where this A0 is connected with an OR gate. 7432 is an OR gate, and now BHE is for higher bank selection. So chip select of this particular memory, odd memory, is connected to BHE and the decoder. So this is what the decoder you have, right? So you have to start with, so the address lines of this one is connected to address lines of this, data lines of this is connected to data lines of the processor. And coming to the connection of this output enable, write enable, and chip select. So this chip select means this memory has to be enabled. So this is odd bank, so this can be enabled by BHE, and then this is even bank, this is can be enabled by E0. So these two signals are used to select this, and this is done through 7432. So this is done through 7432. Right. So now if you consider this, Y0, Y1, Y2, Y3, Y4, and this is what the decoder is initially to look into. So now one more thing, what is asked in the question is that memory mapping should be of 07FFFF. So now this 07FFF means, this whenever the processor releases this address, then that should go to the memory. So now if you try to see this, now here you have memory read and memory write. These are the two signals from, here is your processor, this you connect it to write enable. So memory write, you give it to write enable, and then memory read you are connecting to output enable. So how do you generate these two signals? So memory read or memory write, this can be generated by using this particular logic. So here you have an OR gate, here you have an OR gate. So read bar when it is 0, and then this is I0 by M bar is a pin of 8086. So when it is 0 means it indicates the processor is doing memory operation. So it should be 0. So when it is 0 and 0, then when read bar is 0 and I0 by M bar is 0 means the processor is performing a memory read operation. So here this MEMRD means the hardware is this. That means you should have a OR gate, and OR gate is connected. So when write bar, if it is 0, so then this 0 and 0 means memory write operation, it can perform it. So you can connect this memory read and memory write, both logic signals you can generate by using OR gate, right? And now here you have like lower byte and a higher byte. So here you have a lower odd byte and then higher byte. So further it can be memory read is what you can try to take, and then BHE is what the bus enable of the processor. These two can be given to an OR gate. So this is what the circuit we are now trying to see. So here you can, when it is 0 and then when it is 0, then odd bank is what it is going to be selected, and then memory. So that means writing into upper or writing into lower is what can be decoded like this. This is A0, and then this is how it can be selected. So now what exactly happens here is, now let us have a glance. Here you have an A0 and BHE selection for memory selection. Means chip select, memory chip selection, and memory bank, if it is even or odd, that is D0, D7. Now if you try to give a glance of 8086, how a byte or word transfers on the data bus is. So now if you try to see here, byte transfer to or from even address location. That means now you are going, you are reading a byte from the memory or writing a byte into the memory. And that memory, if it is an odd address, then what happens is, so when the microprocessor transfers a byte to or from an even address location, the address bus carries 20-bit physical address, but the D0 to D7 lines of the processor carries the lower byte of the processor, and the D15 to D8 lines are in high impedance state at this time. So the signal on BHE is high and A0 is low, indicating you are reading from even bytes. Okay, and it enables an even address memory bank and disables the odd address memory bank. So this is how the moment when you are reading or writing into an even location, even address location, so then your D0 to D7 carries the byte, and your D5 to D8 to D15 will be carrying the high, that will be at a high impedance state. And coming to this, A0 should be low and BHE should be high. So it is enabling the even bankers. And coming to the O transfer to or from even address location. So at that time, what happens is the signals BHE and A0 are low. That means you are reading a word. So then word means 1 byte from even band, 1 byte from odd band. Both should be read at a time. Okay. So now if you try to see here, so byte transfer from here word transfer, if you try to see, your 20 bit address lines of the processor will carry the physical address, and lower byte, the lower order byte, right, and D5 to D15 lines of the data bus carries the higher order byte, and D7 to D0 will carry the lower order byte, and these both signals are 0, 0, 0. And now byte transfer from odd address location. So this you have to take very careful. So here at this case, A0 should be high, B bus high enable should be low, indicating that enabling of your higher byte memory locations. And now for a byte transfer from 2 or from an odd address location, the address bus carries the address, but the D8 to D15 lines of the data bus carries the data byte. D8 to D15 will carry the data bus, and the D0 to D lines are at high impedance state. Okay, so it enables odd address memory banks and disables even address memory banks. This is how you read a byte from starting with an odd address location. Then how do you read or write a word from the odd address memory location is? This is what the difference you have to very clearly understand. If the given address is, now let us take 1 0 0 0 1. If the address is odd, then what happens is for word transfer to from odd address location, the processor performs 2 bus cycles. In the first bus cycle, the address bus carries the address of the lower order byte. So in the first clock cycle, the address bus carries the address of the lower order byte, and D8 to D15 lines of the data bus carries the lower order byte, and D0 to D7 lines are in high impedance state. So this is what happens in first bus cycle, and then the signal on BHE is low and A0 is high at this case. It enables the odd address bank and disables the even address bank in the first memory bus cycle, first bus cycle. And then the second bus cycle, it carries 1 more byte. So if you want to transfer a word from odd address location, it performs 2 memory cycles. So now the same thing is illustrated in terms of this. Now if you try to see, if the data segment register is having F000, so then move AL comma FF51. That means moving something into AL, and the memory location, if it is odd, so then it is only byte operation. It takes only 1 memory cycle, one machine cycle. And move AL comma FF2. So here even byte, it also takes 1 memory cycle. Move FX comma FF70. Even word takes 2 machine cycles. It means here accessing a word is treated like accessing 2 bytes regardless of whether the address is odd or even. This is this is in the 8-bit CPU. This is what we are discussing about 8-bit CPU. But now if you consider the same thing with 8086, now this is with 8-bit microprocessor we are talking about. Move AX comma FF91 odd address, it takes 2 machine cycles. So this is with 8-bit CPU. The same thing if it is given accessing it with the 16-bit CPU. So then if you have move AX comma F617, so then in first memory cycle, it takes from the lower byte from this, the next machine cycle, it copies the byte which is at FF618 in the second machine cycle. So that is the advantage. Here, if it is a 16-bit processor, in all cases it takes, from even word also it takes one machine cycle. But whereas in odd, if the addressed location, if it is odd, then it takes two machine cycles. So accessing a word with an even address takes one memory cycle, and accessing a word with odd address requires two memory cycles. Right? So this is what with 16-bit CPU. And this is how you have to draw your 8086 means based system memory circuitry. So now this is you should have two RAM chips. Okay, so then you should have EEPROM, and you have latches transceiver, and here is what your control signal generation is, right? So, and here in this case, this is in minimum mode. This is what we have seen. Now coming to the memory interfacing to 8086, then how to map. Here in this example, we didn't exactly consider how it is like 00. So this part is what not we discussed earlier. Every other part is what we discussed. So now let us try to see how to map a particular address so that your decoder can select that particular or it can assign that particular address to a memory location is. So here now let us try to see, coming to the decoders, what exactly is these decoders are. So the 8086 processor can address up to 1 MB locations and 64 kilobytes IO ports. That means 1 MB is the memory you can connect, and 64 IO devices you can connect to 8086 processor. However, 8086 based system does not use all the memory locations and IO ports. So a memory map for the system specifies utilization of the memory space by the memory device, and IO map for the system specifies utilization of IO space by the IO devices. So address decoders enable splitting of memory into IO space into comfortable blocks and use separate device for each block. So here we have to discuss about a concept called the memory, how exactly you are using the memory addressing system is what we are using in 8086 or Intel based system is what we need to see now. So now let us try to now let us see. So now let me take the memory. So here Intel. So Intel uses the memory, memory mapped IO and IO mapped IO. There are two ways you can give addresses to the memories or IOs. So they are memory mapped IO and IO mapped IOs. So coming to the memory mapped IO, Intel follows IO mapped IOs. So IO mapped IO means here Intel gives different address. Intel gives different address for memory and IO. This is about Intel, which is called IO mapped IOs. And other manufacturers like Motorola and all, they follows memory mapped IO. That means memory and IO both shares the same address. That means there is no separate address, the same address. Now if you have 10001, if this is the if you are giving for a memory location, then you can give 10002 to an IO. So this is what is memory mapped IO is. So Intel follows a IO mapped IO memory mapping, and other manufacturers, they follow memory mapped IOs. So this is the difference, is what you need to see. So now if you try to see here, the addresses, how do you give to memories and IO? Here we use address decoders. We use address decoders to map or to give these addresses to the memory locations. So here we use the decoders can be OR gates, or they can be a 2-line to 4-line decoder or something. So now if you try to consider 2-line to 4-line decoder, a simple n-line to 2 power n-line decoder has n inputs and 2 power n outputs. So it decodes n-bit binary code applied on its n inputs and activates 2 power n outputs. So now if you try to consider, you have 74LS139 is a dual 2-line to 4-line decoder. So here you have 2 inputs, and you can enable either upper section or lower section by using this G bar. When it is 0, then this will be selected. So these 2 lines can be 00 or 01 or 10 or 11, so that this Y0 or Y1, Y2, Y3 can be selected. So this is what the table for your truth table for your 74LS139, and the widely used decoder is 3-line to 8-line decoder. So this 3-line to 8-line decoder, if you consider, here you have A, B, C or the select lines. So if it is 0, 0, 0, if it is 0, 0, 0, then Y0 is made low. So then Y0 is made low. And if it is 0, 0, 1, if it is 0, 0, 1, then Y1 will be made low. Decodes like this. And this chip, if it is selected, if G1, the G1 should be 1, and G2 A bar should be 0, and then G2 B bar should be 0. So when this logic is true, like 1, 0, 0, then 74LS138 is enabled. And based on the select lines here ABC, then any one line will be decoded. Now let us take, if ABC is 101, so then 101, that means here Wi-Fi will be made 0. So Wi-Fi is made 0. So this is what 3-line to 8-line decoder IC's truth table. So now here a simple decoder design, if you try to see, here A4 to A4, A15 and A16. So these can be like, the splitting of 128 kilo memory locations in the address range from 0000 to 1FFFFF. So this 0000 to 1FFF is of 128 kilobytes, and this 128 kilobytes can be decoded on this, like, if it is, here, if it is 0, 0 and 0, then Y0 can be selected. This is wrong. So you have 03FFF. 03FFF. This one F is extra. So 03FFF is what you can consider it. And 07FFF. 04002, this one. So when it is, 001, or when you consider this as 001, this one. So you can split. This is how you can map the addresses, right? And then A17, A18, A19, So A19 when they are 000, so then when they are all zeros, in this case, for this case, A17, A18, A19 are all zeros. So this is an OR gate. So when it is 0 and 0, then this particular memory IC will be enabled and then G1 should be connected to VCCS. So now let us try to see in detail about an example. So now here A15 and A16 and A17, if you try to see for this kind of example, so then here you have 0FFF and then encoding this complete of 1 MB memory locations, you have 4 decoders you can use. Now let us try to take an example. So this is about dynamic RAM interfacing. So dynamic RAM interfacing in SRAM or dynamic RAM, both you can interface this way. Here you can use 74LS139 as a decoder IC, and again each one can be of 2 and then memory read and memory write is what you can give us. Now coming to the EEPROM 2716 IC is what EEPROM. So in EEPROM interfacing it will be the same. It will be the same, but only the difference is here you will not have any writing into EEPROM. You can only read. So it has output enable and then chip select, address lines and data lines. Only write enable will not be there and everything will be the same. So lower byte can be selected with your A0 and higher byte can be selected with BHE. And memory read and memory write, here in this case, you have to generate only one control signal, that is memory read. Memory write, anyhow we are not going to generate it because this is EEPROM. Only we can read into, we cannot write into EEPROM. So that is the difference. Now let us try. This is what EEPROM interfacing. And now here it is, how 8 memory chips are interfaced with 8088 is what it is shown. And with this memory addressing, memory decoding circuit. So now let us try to see this in detail. How do you interface memory like SRAM or EEPROM or all together to 8086 microprocessors? So now let us try to take this particular example. So the example is design a 8086 base system with the following specifications. Then 8086 is in minimum mode. Right, and then you have to interface 64 kilobytes of RAM and 64 kilobytes of EEPROM to 8086 system. And here the available chips are 32 kilobytes chips. And the memory mapping which you need to give for the 64K and 64K is RAM should be given 30000 to 3FFFFF and EEPROM should be given an address of F000 to FFFF. So 4 zeros to 4F is of 64K. So now you have to connect 64 kilobytes of EEPROM, 64 kilobytes of RAM to 8086 system. So now draw the complete schematic of the design indicating of the address map. How do we do it? Is what now we will try to see. Okay. So now how to start? This is the 8086 base system minimum mode. So the minimum mode means your 33rd pin should be connected to plus VCC. And you have like BHE bar and A0 bar. So here you have 64 kilobytes of RAM. So now let us try to interface RAM. So A0 and BHE. So here two signals we can use to even bank and odd bank. So 8086 memory is segmented into even bank and odd bank. So we have two chips of 32K each, which is of 64K. Right? So two RAM ICs are there and two EEPROM ICs are there. Each is of 32K and 32K. Now we have to map the address, like the RAM location should be mapped like 3000 to 3FFFF. So this is what the problem given. So what we can do is Like here 64, so 32K memory chips are available. So 32K means K is 2 power 10. So here you have 2 power 10 and 32 means 2 power 5. So how many address lines each memory IC has? 15 address lines each memory chip has. So 15 address lines memory chip it is having. So 15 address lines. And coming to the data lines, you have 8 data lines each IC has. So 8 data lines. So each data lines. And here you have another 3 control signals, chip select, and you have write enable, and you have read enable. These are the signals we need to connect it to the microprocessor. So now coming to the RAM, this is what things we need to consider. So now what we do is we use A1 to A15. So A1 to A15 address lines of the processor, we connect it to 15 address lines of the RAM chip of even and odd band. And D0 to D7 of the processor is connected to even band, and D8 to D15 of the processor will connected to the odd band data bus. So these connections are over. Now what should be connected to chip select and what should be connected to write enable and read enable is now let us try to see. So this chip select, so here you have another address lines of the processor. That is of A16 and that is of A17, that is of A18 and A19. Okay, that is of A19. And the address is 300 to 3FF maximum if you consider. 3 means 0, 0, 1, 1. So 3 and then all zeros here, 4 zeros to 4 Fs. So here this will be connected to your this should be connected to A1 to A15. So A1 to A15 or 16 address lines. So this 16 can be connected to that particular pin. Now if you try to see here the memory mapping, so even chip, even bank of RAM is 3000. So the entire address, if you try to write here, it should be 0. It should be 1. It is 3. So no. Here, yes. So it is 1. Here, if you try to see 3000. So 300 means yes. So it should be 1, 0. So here A0 anyhow, A0 is connected to this lower band. So it should start with all zeros to all Fs. Okay, all Fs. Right. So here all zeros to all Fs. And this will be 0, 0, 1, 1, 3. And this should be 0, 0, 1, 1. So this is A16, A17. So here is what we have seen. A16 is 1, A17 is 1, A18 and A19 are 0, 0. A18 and A19 are 0, 0. So these are 1, 1. So that means when this address, A16, A17, A18 and A19, when they are 0011 to 0011, that means here this is all zeros to all Fs. So here if you consider the lower bank, if you can consider this as 3FFE. So E means here, the last address of 30002 3FFE. This is even bank address, the last address is. Right, so then this is 0. Right, and then this is 30001. Odd address would be 30001 to 3FFFF. Like 3FFFF. So this should be 1 and then this should be 1. Right, so then it is 3, yeah, this is 3, then it is 0, 0, so this is 1 0, this is another 0, this is another 0, then this is 1. Right, so 30001 to 3FFFF. So now here, so A16, A17, A18 and A19 if you consider. So we are discussing about RAM 1 and RAM 2 interfacing. So whenever this is 0011, then that should be given to the decoder, and then decoder should indicate this memory location as, or this map this address. So now if you try to see here, you have A17, A18 and A19. You are giving it to the latch, and then here you are giving it to an address decoder 74LS 138. Right, so 138. So here 74LS 138. And here is what your 62256 RAM memory location. 62256. So here this will be even bank. So this will be even bank. And then this is your odd bank. So even bank and odd bank selection. So now this is given to Y1. So this Y1 of the decoder and A0 will map this memory location. So here if you consider your A17, A18 and A19. So here A16, A17 and A19. So here you have to add A16 and A17. You have to connect it to a NOT gate. So when they are 1 and 1, so here this is A16, so here this is A16. So here you are using A1 to A15. So A1 to A15, A1 to A15. Then you have A16 and A17. So A16 and A17, they are 1 1 here. So when they are 1 1 means we have to get 0. So that means here they are given to a NOT gate. So when they are 1 and 1, the output will be 0. Whenever the output is 0, anyhow by default A18 and A19 always they are 0. So then this is 0, this is 0, and then this is 0, and then this is 0. So that means when it is 1 and when it is 1 and then this is 0 and this is 0. So this logic, this is a latch, it is connected to Z1. So G1 you can connect it to ground also, no problem. So here A17 and when it is 0 0 0, then here this is 3100 is mapped to Y1, and that Y1 you can connect it here to even bank of the memories. And similarly, odd bank can be connected to Y7. So here Y7, the moment here you try to see, so the odd bank address 000 and the decoded line here. So this will be, the moment it is odd address. Now the odd address, if you try to see 0011, but here the address is something different. So here it is 1 and here it is 1. So odd bank is what need to be considered. So this can be given to a decoder IC, and then the decoder signal can be given here, right? So this decoded these lines can be given here. So this can be selecting odd RAM location is. And here this is 74LS138. So you can use 74LS138 IC, or you can use a simple OR gate. So you can use read bar and write bar and M by IO bar. These three signals can generate memory read and memory write. So this memory read and so memory write, you can connect it to write enable of both RAMs, and memory read you can give it to output enable is. So memory read you can give it to output enable is. So memory write is connected to output enable, right? And then so this is about RAM. This is about RAM and RAM interfaces. Okay, and here you can use a simple OR logic which I discussed earlier. So you can use the same. And here you can use address latch and then address decoders. That also you can connect here. And then this can be in minimum mode, VCC you can connect here. So this is what about the memory mapping of even bank, right? So here BHE bar, so it should be low for odd, and A0 is what should be, it should be high for this one. And A0 should be connected here, so you have to connect A0 here. So A0 is anyhow 00, so that indicates it is an even memory location S. So similarly, you can give like F000 if you can consider. So F000, that means A19, A18, A17 and A16, and A19, A18 and A16, they are always 1111. So here in this case, then the address is F0000 is even, and this is FFFFE is the last of even bank of EEPROM. And here in this case, F0001 and FFFF. So this is what the odd address. So now the A16, A17 and A19, they are like this. So then you have a memory decoding logic, here in this case A18 and A19. So A18 and A19 if you can consider. So A19 is 0, so then when it is 0, then you can give it to a latch and then you can design a decoder circuit, and which you can take it here. So when it is odd, it can identify this, right? So this is odd, and then this is odd memory location, and then here you can only connect memory read. So memory read means output enable is connected here. So and then for even and odd, you can consider here this BHE bar. So BHE bar is for selecting your odd band, and A0 is for selecting your lower band. So this is how you can map. This is how you can design a. This is how you can design a. Or how you can map a memory address mapping is. So this is what the problem, like you have you are interfacing memories like EEPROM and dynamic RAM both to 8086 processors. This is what one example, and this is how it is mapped. So now let us take one more problem. Interface 432K EEPROM and 432K RAM to 16-bit data bus of 8086 base system. Design address decoders. Okay, design address decoders, assigning the address range E000. So that means if EEPROM, see, always remember here you have Intel based systems, computer systems. So here the RAM and ROM, if you try to consider, the design your own systems, no, one simple microprocessor based systems. Now this is what the example we are considering. So here you have, so this is what the problem given to you. So now what you need to do is interface 4 32K EEPROMs and 4 32K RAMs. Right, and then but EEPROM should be mapped to this address, and then RAM should be mapped to this particular addresses. So now let us start how doing all this. Then the resultant one is this. So this is what you need to do. Now let us try to understand what exactly it is. So now this 32K. So 32K means it is similar like what we have discussed. So you have 15. So now this is RAM 1, RAM 0, and here you have RAM 2 and RAM 3. So total 4 RAMs are there, and each RAM is of how much size? 16K. So 32K, sorry, 32K. So 32K means each RAM is having 15 address lines, and each RAM is having 15 address lines. So these 15 address lines can be connected to A1 to A15 of the microprocessor. A1 to A15 of the microprocessor is. So now, so this A1 to A15 can be connected to RAM 0. This is lower band. Okay, this is lower band, and then this is what odd band of 10002. So now if you consider this 10002 1FFF, this is 64K. So here total memory is, so F into 16 power 0 and F into 16 power 1. And so this is 64K, and 1FF would be 16, right? So so here the total memory would be so here F into 16 power 2, F into 16 power 3, F into 16 power 4 plus 1 into 16 power 5, 1 into 16 power 5. So that those many locations, you are going to give the addresses. So then the whole, the memory RAM. So then this is what RAM 0 and RAM 1. So this is 32, 64K. So this is 32, 64K. So total 64K, 128K. So that means you are going to interface 128K of RAM. But the only thing is you don't have direct 128K and 264Ks. You have memory ICs of 32K. So then when they have 32K, then you want to make it to the RAM location of 128K. Then 4 chips has to be used. So 4 chips you are using. So here 32K means A1 to A15 is what you are going to use. And here A0 is given to OR gate, and here this is what your decoder IC is. Here is what your decoder IC. So A0 and then BHE bar. So BHE bar, this location. So Y1. So here if you try to see very clearly, Y0 is connected here, and Y1 is connected here. So that means Y0 is related to this. So Y0 is related to RAM 0 and RAM 1. So the lower, that means 32K, 64K means 0F 00002 0FFFF. Then 10000 to 1FFFF. That is of 64K. So this location, this memory, you can map into 0, 0, 0, 0, 0. This RAM 0 and RAM 1 to 0, F, 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 F is. Right. So this A16, so that means if you try to see A1 and A15, anyhow these are connected. Right. A1 and A15, these are connected. A16, A17, A19 and A19, they are always zeros. So these zeros, A19 is given to this 0, always it is 0. So this is connected to Z2 A bar and Z2 B bar. And A18, A19, A17 and then A16. So they can be of 0, 0, 0. So when it is 0, 0, 0, Y0 can be selected. And then the next one is the next RAM location. This RAM 2 and RAM 3 are the next 64K locations. So then at that case, you can try to see this is 0, 0. Sorry. So this can be of 1 F. So that means 1, 0, 0. The next location is 1, 0, 0, 0, 2, 1 F. F, F, F. So this is what the higher byte. That means this is of the location of this RAM 2 and RAM 3. So here you have 1 and 1. So when it is 1 and 1, so here if you try to see, when A16 is 1 and then rest all are 0, so then Y1 is selected. So when Y1 is selected, so this particular line is given to A0 and BHE bar of this particular chip selection. So this chip selection point, if you try to see, so this decoder, this address is this decoder pin with BHE and A0 are selecting 6256, 6256 of RAM 0 and RAM 1 when it is Y0. And when it is Y1 means what? When it is 1000 to 1FFF, so then here this 1 would be A16. That means 1 A16, rest all 0. So then when the rest are 10, when it is 100, Y1 will be selected. So when Y1 is selected, these RAM locations are going to be selected. Is it all right? Yeah. So now here D0 to D7. D0 to D7, so RAM 0 and RAM 1, it is connected to D0 to D7 of the processor, lower, and odd is selected to D8 to D15. So address lines and data lines are connected. Then you can select these memory ICs, chip select to the memory decoder so that this particular address is mapped. So this can be done through 74LS138 decoder IC, and the decoder IC, the pins, if it is of 32K, A1 to A15 are gone. So A0 is what to select this lower band. So here you have to connect A0. So A0, so here when it is 0, then this is 0. So when it is 0, then even band is selected. And when it is 0, so then this is 0. So then when this is 0, odd bank is selected. Right? So this is how you can map 4 SRAMs. This is how you can map 4 SRAMs to 8086 base system. So here is, if you have two 64K ICs, then this will not be the problem. But here the constraint is what? The available RAM ICs for you are 32K. So 4 are there. But you have to map this address. So then here 4 RAM ICs need to be connected. So 4 RAM ICs you are going to connect here like this. And this memory read and memory write, you can use read bar and write bar and I0 by M bar with OR gate. You can generate this memory read ICs to this. So this memory read ICs, memory read bar and memory write bar, you can connect it to write enable and output enable very clearly. So the memory read bar, if you try to see here, this is connected to output enable, and memory write bar, it is connected to write enable. So all the pins of memory IC are connected to 8086 processors. So this is how you can interface a dynamic RAM to your 8086 base system. And similarly, the problem is what? Interface 432K EEPROMs and 432K RAM to 16-bit data bus of 8086. Not only EEPROM, RAM IC, you have to connect EEPROM also to store your monitor programs. You have to connect EEPROMs also. How many EEPROMs are there? 4 EEPROMs of each of 32K, 32K. But the address which has to be given to this is what? E0002FFFF. So here, the lower EEPROM can be given E0002 EFF. So this is the 2 EEPROM should be given this address. The next address is what? F000002 F. So this is of 64K and this is of 64K. So this is of 64K and this is of 64K. So this 128 kilobytes of EEPROM, you have to connect it to 8086 processor. So here you have 32K, 32K. Two ICs are available. So one you can use it as a lower band and one you can use it as odd band. So now the address, if you try to consider E000, so E00 means here you have 1110. So 1110 is your E0 and 1110. So this is, and then this is all zeros to all ones. This is from your, you leave your A0 and you have to start from is what? A1 to A15. So A1 to A1 to A15 are all zeros. Right, and all ones. So A0 can be 00 in case of 132K, and odd band means BHE bar is what you have to connect this. And coming to the upper one, now if you see, this should be 1, 1, 1, and 1. So here, this A16 line is what only the difference is. So A16 line, if it is 0, 0, 0, but in the case of here, it is 1. So this is all zeros to all ones, right? So this is now the same thing should be here. Now if you try to consider, you have to take one more LS, one more 74LS138 decoder IC, and here you have A16, A17, A18. So then in all the cases they are here 0, and here in this case of lower EEPROM 0 and EEPROM 1. So this is EEPROM 0 and EEPROM 1. So this is 0 and rest all are what? 1, 1, 1. So when it is 0 and when it is 1 and when it is 1, so when it is 0, 1, 1, right, 0, 1, 1, and then A19 is also here, A19 is connected to G1. So then in that case, Y6 is going to be selected. Y16 is going to be selected. And when it is 1, 1, so that means it is 1, 1, 0. So when it is 1, 1, 0, so Y6 is going to be selected. When it is 1, 1, 1, Y7 is going to be selected. So this Y6 and Y7, so Y6 is related to the lower band of this. So this Y6 should be connected here along with A0, and BHE, and Y7 is related with the higher address of the EEPROM is. That is only the difference. It is everything will be the same, but only thing is coming to the mapping. Here the address would be like always A16. Here you have 100. So when it is 100 or when it is all 00, so Y0 and Y1 is going to be selected. But here, when it is 110 or 111, Y6 and Y7 they are low, and this Y6 and 17 then they are low, then chip select is what going to be made 0 along with your A0 and BHE bar with simple OR gates. So the design logic here is, here, so 4 OR gates, but here no place, so that's why here you have 2 OR gates here for this and 2 OR gates for this here, but all 4 gates is drawn here itself. So now only the difference is, you have to, when address is given to you, you have to be very clear in mentioning like what exactly you are going to get and all. So this is all right. So now and everything would be same, but when it is EEPROM you have only output enable. When it is output enable, only you can connect memory read only. So this memory read only you are going to connect. So this is memory read only you are going to connect, because you cannot write into EEPROM. If it is flash then you can write, but this is only EEPROM. So this is how you can connect. So you can interface your RAM and EEPROM to 8086 processor system. So in detail, similarly the previous example which I have shown you for this, so you can have a decoder for your RAM and ROM, or otherwise you can use here Y1. So Y1 for, yeah, you can use the same thing, Y1 for your lower RAM and Y7. So when it is 1, then this Y7 will become 0. So when it is 1 and 1, so then you can use this Y7 to your EEPROM. So Y7 to your EEPROM and Y1 to your RAM IC. So this is what the decoder logic is, what you can connect is. This is only the differences. Earlier when we have seen, so this system, so then here you have FFFFF. So this is what you are, when it is 111, A16, A17 and all, when they are like A16, A17 and A19. Anyhow A19 if it is 111, then 111 is what you can try to make it here. So A19, directly you can connect it to A18. So how do you connect? That is what the difference is. So A17, A18 and A19. So when it is 0, you can connect directly to Z1 bar. So how you are connecting your signals here matters. So here you are selecting your Y1 or Y7. So here Y7 is for odd. So these two examples very clearly explains like whether you are interfacing 2 RAM ICs and 2 EEPROM ICs, or 4 RAM ICs and then 4 EEPROM ICs also. Very clearly you can interface memory chips to your 8086 processor. So what we discussed in this particular lecture is like how can you map a particular address to your RAM. This RAM IC is like a empty land kind of thing where you can write or read. So empty land, if it is assigned to you to construct a colony, you can construct homes over there, but whenever there is a letter by post, it should be reached to each that particular corresponding person. So then what you are trying to do here is, each house you are constructing open plot and each house numbers is what you are allotting. Here also same thing we are doing. Have empty RAM ICs, and this empty RAM ICs we are going to give addresses. Though those addresses can be any addresses, as we have seen here in this example. For EEPROM, like Intel follows the lower addresses for the RAM and upper address E002 EFFF is for monitor program. So then in that case, then how to give addresses to those memory ICs is what we have seen here in this particular example. So now if any size of any RAM or EEPROM is given to you, So, the same thing here, the same thing is duplicated here, or otherwise you can use here Y7 and Y6 directly here to the OR gates. No need of using the separate IC. The same, this IC can be used because, the moment it is just like they are different, the decoder is showing Y7 and R. So from this you can plot. This is what memory interfacing is. So microprocessor and interfacing, now if you try to see, connecting in a compatible manner. Connecting in a compatible manner is called interfacing. So now we are interfacing memory chips. The memory chips could be your RAM ICs or EEPROM ICs. RAM can be of SRAM or DRAM. Anyhow, both would be the same. So now we have seen a complete scenario where we can interface and then we can give addresses to the memory location. So whenever the processor gives addresses, that particular address, that particular location of the memory is connected and byte is fetched from the memory or IOs. So that is what we have seen in this particular class. Okay. And now in real time, where do we use it? Yeah, in real time, your IBM PCs, all your IBM PCs, your RAM of 64K, 640 kilobytes is given these addresses. So the moment you try to see these addresses on your computer, then the addresses now, if you can try to see here, the RAM 64 kilobytes, the first 1K is used for the interrupt vector table. So the IBM PC based systems will have your RAM locations like this. So now you can see the practical application of what we have discussed now. So 00400H to 004FF is set aside for BIOS temporary area. 005FF is set aside for the temporary storage for certain parameters in DOS and BASIC. And a certain number kilobytes is occupied by the operating system itself. So now A002 BFFFH is video display RAM 128 kilobytes and a total of 128 kilobytes is allocated for video, and C002 FFFH is used 256 kilobytes for ROM. Right, so this is for BIOS ROM, basic language compiler ROM, hard disk controller, other peripheral board ROMs, and other test expansion by the users. So IBM PC uses addresses mapping like this. So after finishing this lecture, if you try to see any advertisement for the computer which you have to buy, then they will be mentioning these addresses kind of thing. Now see, the processor which I want is very important. The first requirement when you try to see the advertisement, the processor is whether it is i3 or i4 or i5 or i3, i5 or i7. But and the second next thing which you find very important is RAM, how much size of RAM. So these days we are using for our laptops, our systems, that is of 4 GB or 8 GB or 16 GB. So the moment the memory increases, the cost, how it is increases, and then the significance of that is what we have to understand, like how our systems are. So this is what our IBM PC memory map, it is given, and then this is what so IBM PC memory map, for your computers when it is varying from PC XT, extended technology, PC, advanced technology. So the BIOS date of, it is mentioned here, 86 and all, and the model of that, and the memory locations, and these memory locations are used for which kind of applications is what we have, what it is shown here. Okay, so in real practical systems, how this is given is what we have seen now. So now I think you are very comfortable, like if this kind of problems, if it is given to you, this problem also you can revisit, like giving of 64 here, 64 kilobytes of EEPROM and EEPROM. If the ICs are available, then you can give a decoding things kind of thing like this. Right. So here, when A16 is, A16, A17 and A19. So here, you can you can resolve this, and A19 and all you can use for some Z10 and all, and then you can revisit your problem again. So now this is what an example of, 8 EEPROMs are interfaced with the 8088 So 88 and then your 74 LS 138. So here F002 FFFH and F02 FFH means each is of when it is of A15, A13, A14 and A15, A16, A17 and all can be used. Okay, A16, A17 can be used to identify because they are always zero in this case, F0002, F00, this one, all this case, right? So this is of 64K, 864K EPROMs are interfaced and then their address mapping you can try to see. When it is of 0, when it is of 1, 2, 3, 4, 5, 6, based on your, these lines. When it is of 000, this 001, this 002 is this. Data and address lines you can connect, and this is how you can interface even 2 or 4 or 8 memory chips to your 8086 processor of 1 MB also. So this is what your EEPROM interfacing. Now you can try to see like what would be, this is a 4K by 8, 4K by 8, 4K by 8 and 4K by 8. 4K means here K10 and then 2, so 12 address lines, so A0 to 11, so A1 to A12, 12 address lines are used for this, and rest of the address lines can be used to decode the mapping addresses. Okay, mapping address. So this is FC00 to FDFFH and FE00 to FFEH of 4 EPROMs are interface to 8086 microprocessors. So now you can take on some example like this and then you can try solving, and how to interface SRAM and EEPROM with 8086 processor is what you can clearly practice. And a few examples I think I can give you in the next class, and possible it is there in my slide, I can show you, and this is what the practical application of this. And with this we will conclude today's lecture, and IO port design is what I'll try to discuss in the next class now, because now only 5 minutes is there. So port and port programming and 8255 IC, how do we interface to 8086 processor is what we try to see in the next classes, right? So if you have any questions, I think we can take up if time permits. And if I can see you, I think we can, like, you can even understand now, so that, any system, based can be designed. So is that all right? So we'll meet in the next class with port programming and port